To create even modest Java programs, we're going to need a way to store and manipulate information. Our chief resource when doing this is the variable, and that's what we're going to be taking a look at today. To begin, let's create a new project in NetBeans. I'm going to call mine variables. And this time, we'll allow NetBeans to create the main class for us so that we can get coding as quickly as possible. I'm going to delete these comments here just to keep everything as readable as possible. And now we're good to go. The first computers were little more than calculators, and Java, of course, retains this functionality. For example, Java can evaluate this statement 1 plus 1, which of course will evaluate 2. However, Java is pretty complicated and designed to do a lot of different things. So we need to provide context to our commands. Here, if we tell Java that we'd like it to print the result of this statement, our program will run as expected. In addition to some others, Java can perform all of the basic arithmetic operations. It can do addition, subtraction, multiplication, for which we use the star, not the X on our keyboard, and of course, division. If we run this program, we'll see 4 print line commands, all of which give the proper evaluations of these statements. We can, of course, change these numbers to be any combination of numbers we see fit. We could, for example, run our program with the input of 2 and 3. Changing these lines manually, of course, is kind of a pain and quickly becomes infeasible if we're writing very complicated programs or dynamic programs that take user input. Fortunately, programming gives us a way of storing and retrieving data. This is called the variable. To declare a variable in Java, we first have to specify what kind of variable we're going to be using. Variables come in a number of different types. In this instance, we're going to be content using simply whole numbers. That is, numbers that do not have a specified decimal place and aren't fractions. And in this case, it's appropriate to use one of Java's primitive types. These are essentially as base level as you can get with information in the Java programming language. Just about everything else we work with in Java is built out of the primitive types. To declare a variable of the integer primitive type, that is whole numbers, we use the keyword int, all lowercase. Once we've done that, we then need to give our variable a name. This is a unique identifier that we'll use to access this piece of information in the future. Each variable in our local program should have its own name. Let's call our first variable x and our second variable y. We've just written 2 perfectly legitimate lines of Java code. If we run our program, we're going to see the same output we did before, but behind the scenes, Java will also be setting aside memory space for our variables x and y. This allocation doesn't affect our print line commands because the variables are not referenced in them yet. So let's store some information in our variables. To reference a variable once we've created it, we simply reference it by the variable's name. It's important that we not try and reference our variable by typing int x again, because rather than accessing the existing variable x, this is the command for Java to create a brand new variable x all over again. Once we've referenced our variable, we can change its value by using the equal sign. So let's set x to 4 and y to the number 3. Our print line commands currently operate with 2 explicitly declared integers, the numbers 2 and 3. Since x and y are also integers, it stands to reason that we can simply replace the existing numbers with the variables x and y. When our Java code comes to the variables x and y, it will look to see what integer value they have currently been given. It will find the numbers 4 and 3. So if we run our program, we should expect this first print line statement, x plus y, to evaluate to 4 plus 3, which then of course evaluates to 7. And that's exactly what occurs. So here's something interesting. The last line of our program, in which we divide x by y, isn't quite evaluating as we might mathematically expect it to. In this line of code, x has the value 4, declared in line 9, and y has the value 3, declared in line 10. 4 divided by 3 is 1 and 1/3, but our program is simply outputting 1. That's of course because 1 and 1/3 is not a valid integer value. Integers are only whole numbers and never fractions or decimal place numbers. So, to keep us working with integers, Java simply rounds down any calculations that have fractional portions to their nearest whole number. If we wanted to be working in an environment where we could have fractional results, we would need to use a primitive type other than integer. Now that we've set up our print line commands to take integer input instead of explicit numbers, we can modify the behavior of all 4 lines of calculation simply by changing the value of these integer variables. For example, if we wanted our program to run on the inputs -10 and 5, integers can be negative, they just can't have fractional components. All we need to do is change the values we give to our variables on lines 9 and 10. If we run that quickly, we see the expected results. Okay, awesome. We've just learned the very basics of working with both integers and variables in Java. In the last couple of minutes here, let's go over an edge case and learn a little bit more about how Java thinks. You might remember from earlier, I was talking about how Java sets aside memory when we declare new variables. This is one of the huge advantages of working in a high-level programming language like Java. Java abstracts away, or does automatically, most memory management for us. Oftentimes, this lets writing programs be simpler, and we can write shorter, cleaner, more easily readable code. Of course, it is important that we appreciate what's happening behind the scenes, lest we run into issues. For example, whenever Java sets aside memory for an integer variable, it's going to set aside the same amount of memory for all integer variables. That means there's a maximum and a minimum value that Java could ever conceivably store in an integer variable. That's these 2 numbers right here. Maximum integer value, minimum integer value. So let's do an experiment. What happens if we attempt to store and print out an integer variable that is 1 larger than this maximum value here? To start with, let's simplify our program. We're simply going to assign a value to the variable x and then print it out. If we attempt to assign a value 1 larger than possible to the variable x, NetBeans is going to yell at us. It's got some logic built in that attempts to stop us from making this very basic and common mistake. If we were to attempt to compile this program, we would also get an error. However, we want to make this mistake in the name of science, so we're going to trick NetBeans. We're going to set the value of our variable x to the largest possible integer value, and then in the next line, of our code, we're going to set the value of x to be 1 larger than x is currently. Actually, there's a nifty little shorthand we can use for this. X equals x plus 1 is equivalent to x plus plus. Okay, so when we run this program, which will sneak by the compiler and the NetBeans, and do our addition at runtime, we should attempt to print out an integer value 1 past the largest integer value Java can store in a memory location. When we run this program, we get this very, very, very negative number. This number happens to be the smallest number that we could ever store in an integer. This makes a kind of visual sense. We've gone so far positive or to the right on our integer number line that we've arrived at the leftmost or most negative point. Of course, in a mathematical sense, this could get pretty confusing pretty quickly. It's unlikely that we're ever going to write programs that will need integer numbers larger than this value. However, if we do, we certainly need to be aware of this issue and circumvent it by, for example, using a variable type that can handle larger values. The long variable type is pretty much just like an integer, but more memory is allocated for it. So when we run this program, we will get the mathematically accurate result.